Enough talking about VLANs and stuff. In this video, we are going to talk about spanning tree protocol, or you can say STP protocol. There is various versions of spanning tree protocol, but the most prior defined version is the version mentioned in IEEE 802.1d standard. Over time, the spanning tree evolved and replaced with many variants of it. I will give a timeline in further in this video, but first let's discuss what the spanning tree is all about. In the last few videos, we have already seen that how much the redundancy is important on a network, but to make a network more redundant, we have to connect a single networking device with use of multiple cables, and there is always a chance of getting stuck in a networking loop. We will talk about the network packets, Ethernet frames in further detail in future, but you have to understand that a network packets contains a deadline of itself, but only at but this deadline starts only on layer 3. So whenever we talk about layer 2 devices such as switch, which forwards frame, there is no mention of the packet's deadline. So the packets keep on forwarding and forwarding, and this just one looping of frame may cause a broadcast storm, which leads to another significant problem, that is MAC address flapping. MAC address flapping may be defined as the instability of MAC address table because the tables keep changing due to the frames receiving from the same source from different ports. This video is about giving you the skeletal structure of the STP protocol and not a deep dive video. If you are interested in getting more details and also solving how STP selects which ports to open and close, please take a look at Kevin Wallace deep dive video, which I'll be posting a link in the description. So it seems like that I have already spoiled the fun of STP. So without any further delay, let's begin recalling what actually the STP does. So the STP spanning tree protocol prevent loops in a redundant network by switching the ports, which means selectively blocking some ports with the help of spanning tree algorithm. So how the spanning tree able to achieve this form of network efficient redundancy is partially defined in the name itself. Just like a tree where all branches of a tree start from a single trunk, the spanning tree makes the network to operate as same as the trunk of the tree. It elects a bridge as a root bridge. The term bridge here signifies the switch. A bridge is an older form of network communication device which is not in use today, but the name still hung up. In this video, by the word bridge we mean the switch, as the spanning tree convention use the term bridge. So a root bridge is elected on the basis of lowest bridge priority. The bridge priority is a term that is to be configured on the switch itself, or if it does not configured, or if it isn't configured, then the switch with the lowest MAC address will be regarded as root bridge. And just like a tree where many branches originate from the main trunk and each branches has its own girth and weight, the links or nodes emerging from this root bridge will have a cost, and this cost is a form of representation of bandwidth. So suppose two bridge or switch are connected with each other using two different speed links. Say for example, one is a fast Ethernet link while another is a gigabit Ethernet link. The spanning tree protocol will decide to use the gigabit ones because it is faster in speed, and the final decision to select which link to be used, the decision is based on depending on lower bridge ID or the lower neighbor port priority or the lowest neighbor internal port number. Let me explain in some detail that suppose two switch are connected with the same kind of 2 gigabit link. So in between link A and link B, which are of both the same speed, which the STP will select. So it will select link A if the neighboring port priority of suppose switch B is lower. It seems that I haven't explained the port priority. It is nothing more significant than the port number itself. Suppose switch B, which is the neighboring switch in this case, has a port number of F01 and F02. It is pretty clear that F01 is a lower number than the F02. So the STP will select the F01 as its current transferring link and the other link will be blocked state. The numbering convention that I just is the final type of decision based on the lowest neighbor internal port number. Before reaching this kind of judgment, we can also configure neighbor port priority on per interface basis on the switch itself. Now I am sure that we have familiarized how the STP works. Now let's take a look on the different port costs according to IEEE. Actually, the port cost is divided on the basis of time because in earlier days there were no fast speed links. The convention itself tells that it used the term bridge, and bridges are known to be not as fast as a switch can be because some switches supports up to terabytes of transfer per second. So to keep it simple, let's start from the IEEE original defined cost, which was from 1998 and before. For a 10 gigabit connection, the port cost was 2. For a 1 gigabyte, the port cost is double, that is 4. For 100 Mbps connection, also known as fast Ethernet connection, the port cost is 19. And for the slowest 10 Mbps connection, that is normal Ethernet, the port cost is 100. To find the latest IEEE port cost, it is far more easier now. We just have to divide 20 billions with link speed in kilobits per second. By 20 millions, I mean the 2 with 10 zeros in it. For example, for a 100 kilobit connection, the port cost will be 200 millions, which is simply subtracting 2 zeros from the 20 billion we've seen earlier. One more example. Suppose for 100 Mbps connection, which itself equal to 100,000 kilobytes, that is 1 with 5 zeros in it, will outcome as a cost of 200,000, the 2 with 5 zeros. Enough learning about cost. Let's have a look about how the STP keeps track of on what state does a port have to be in. Before telling you the mechanism behind keeping an eye on different port states, let me tell you first that the STP maintains various port states. Some are transitionary, some are stable ports, which defines the function they are performing, whether they are sending or receiving data or not, we are listening or learning or flooding the MAC address table or not, etc. Now let's talk about mechanism. So for every 2 seconds, the STP sends a hello message that tells every switch or every other bridge or networking device that he is still the root. Or by any chance, if the devices failed to receive the hello for 20 seconds, that is 10 times the hello. If a device misses the 10 hellos, the switch starts to re-elect the root position, and the re-election will be a two-step process in which each steps will cost around 15 seconds. So after calculating all the cost for the re-election, we have a 20 seconds age timing, then 15-second transition timing, then again a new 15-second transition timing, which will cost total of 50 seconds for a port to switch its role. At this point, an interesting question arises: what will happen if a switch that does not is in any role in pre-earlier form If we connect a device to that port, how much time will it take? So, as we can see that it is earlierly defined that the switch that port was left empty and is not connected anywhere. So the first 20 seconds is worthless for this port as it is not assigned prior to any role. It only takes the transitioning period that is of 2 times 15 seconds each, a total of 30 seconds to get a specified role. Now the time taken to decide a role of a port in a network is known as convergence. The STP takes a relatively longer time to converge, which is 50 seconds as we have just broken down with its default setting, and all the waiting time must be followed. So a new improved version which we are going to see improve the network convergence and was a much needed change as no one wants to wait for 50 seconds just to connect to a network. Continuing the older spanning tree protocol, first let's discuss all the available port states. So there are 5 defined port states, out of which 2 states are transitionary. I will mention whenever they come. The first state is disabled state, in which the port is administratively disabled. Second is blocking state, which is a stable state that actively ignores the incoming data frames and is not to use the forward data. The third is listening state. It is the interim state, or you can say a transitionary state, which just powers the port but does not give him ability to learn MAC address or forward anything. Then the next stage come learning state, in which the port floods the MAC address table by learning the MAC address, but still it has not started forwarding. And finally, the forwarding state. It is also a stable state that allows MAC address learning and forwarding of data frames. I know STP spanning tree protocol is a long mess to deal with, but we are almost on the verge of completing the old protocol. But before wrapping it up, a last thing to know about is the port roles in the spanning tree. The port rules are way more simpler than port states. There are 3 of them. The first is root port, second is designated port, and the third is blocked port, which is itself self-explanatory. The root ports are the port on non-root switch, the external neighbor switch connecting to the root. The designated ports are the ports that are actively engaged in data forwarding, and one thing to remember that the root switch only have the designated port. The neighboring switch has one root port that connects it directly to the root switch. And finally, if the neighboring switch has multiple connection to the root switch, some of the ports are blocked and the blocked port is termed as blocked. Isn't that simple? And we have just wrapped up the earlier versions of STP. Now it's time for a timeline. Cisco has been a significant contributor to the development of spanning tree protocol. Actually, it is the one of the major brands that influenced the networking industry. By the way, the spanning tree protocol was first standardized in as IEEE 802.1d back in 1990s, but it was quite limited in functionality as the all VLANs share one STP instance. That means the load balancing isn't possible in them. And we have already seen the original STP is quite slow in converging. So the Cisco developed its own PVST, that is per VLAN spanning tree, which implements the original STP on the basis of different VLANs, which empowers the load balancing. But the problem with that it is quite limited to ISL encapsulation only. ISL stands for inter-switch link encapsulation. It is an older form of encapsulation done in VLAN which is not used today. So Cisco has to come up with a new form of PVST, that is PVST plus, per VLAN spanning tree plus, which is considered an actual upgrade to A22.1D, the original spanning tree. In this, every VLAN has its own STP instance and can load balance by blocking different port in each VLAN. It also enables the support of A22.1 encapsulation. After some time, in 2001, IEEE introduced a new protocol, a new upgrade to STP, that is RSTP, which stands for Rapid Spanning Tree Protocol, as defined in 802.1W. It improves the converging time far better than original STP, but it still shares only one STP instance. So Cisco has to act, and by making it viable for different VLANs, it creates a rapid PVST, that is rapid per VLAN spanning tree plus, which can do the same but better by doing it separately for each VLAN instance. And the final upgrade to STP is MSTP, which is defined in A22.1S, which is IEEE standard but also supports multiple VLAN. However, configuring VLANs in MSTP is somewhat difficult, so we still use the rapid PVST plus, and we are going to learn about this in our CCNA journey. We are already quite familiar with the working of STP, so learning RPVST plus, that is rapid per VLAN spanning tree plus, should not take a toll on our head. So let's begin, starting from the basic. As I have just made it clear that the every iteration of by Cisco, as I have made it clear that the every iteration of STP by Cisco enables the multiple VLAN support. The original bridge ID decision has to change to include the VLAN information. So originally bridge ID is composed of priority and the system ID. The priority can be configured on the switch, while the switch fill-ins the universal MAC address as the system ID. But in case of rapid per VLAN tree, the priority must be in the multiple of 4096 with added 12 bits of VLAN ID and finally the system ID. So contrastingly, earlier the original bridge ID was of 2 bytes of priority and 6 bytes of system ID. And now, after including the VLAN information, the priority will be in multiple of 4096, a total of 4 bits, plus the VLAN ID, which also known as system ID extension of 12 bits, and finally the system ID 6 bytes. And as we know that the bridge with lower priority becomes the root. So while load balancing, we have to make one switch or bridge a primary bridge, while this second bridge as secondary bridge. When we make a bridge primary, its priority becomes 4096 less than the current root priority, making it the root bridge. And if we configure a bridge to be secondary, it results in that the switch using a priority of 28,672 with assumption that the value will be less than that of other switch, that the use of default 32768 and higher than any switch configured as root primary. So if the primary fails, the secondary takes place rather than any another one. Now let's talk about another change in RSTP that is new from original STP. The thing we are going to talk about is port roles in RSTP. So as we have learned, there is something called root port, which is present on a non-root switch as the best path to the root switch. Second is alternate port, the port that replaces the switch root port when the root port fails. Another type of port is designated port, that is the switch port designed. Another port is designated port, that is the switch port designated to forward into a collision domain. It is the normal functioning port. Next type of port role is backup port, which is a port that replaces a designated port when a designated port fails. And finally, there is disabled port, the port that is administratively disabled. There is a lot of confusion going on between difference of alternate and backup port. So I want to repeat to make it obvious and clear that alternate port is the backup of root port. If the root port fails, the switch wants to reconnect to root bridge again. So it will use the alternate port to re-establish the connection, while backup port is the backup for designated connection or designated port, which means that if somehow the normal working of a switch is hindered or the normal designated port fails, the backup port will act and reinforce the connection. It is a normal functioning port and does not take part in the process of making a route. I hope that I am making it clear. Now quickly let's discuss about the port states. When compared to STP, RSTP has fewer port states, only 3. It is discarding, learning and forwarding compared to STP, disabled, blocking, listening, learning and forwarding. So if we administratively shut down the port, it will go into discarding state, or what we used to say that the stable state in which port is actively blocking the data frames is blocking, but now we call the same state as discarding. So discarding combines the both disabled and blocking state of STTP. What we used to say that port is in listening state if it is active but does not learn MAC or neither forwards the data. We don't use that listening state in RSTP. The learning states remains the same, which is used to flood the MAC address table by the new information, and the normal working that we used to call forwarding still called forwarding in RSTP, which allows both MAC address learning as well as forwarding of data frames. We are about to finish this topic, but before finishing, let's talk about some of the optional STP features that are port fast, BPDU guard, and ether channel. Starting from port fast, it is a feature that enables a switch to immediately transition from blocking to forwarding state for access port or the port connected to the end devices. It helps to faster the convergence time because then switch do not need to transition from first listening then learning states. RSTP by design incorporates this facility by default, while it be manually configured on older switch. After enabling port fast, it exposes the switch to different types of possible security exposures. For example, without listening and learning state, an attacker could connect switch to one of the port first enable port with low STP or RSTP priority and becomes the root switch. So this new topology could have worsened the performance of the desired topology. Even the users could innocently harm the LAN when they buy or connect an inexpensive consumer LAN switch which does not have STP functions, so it can cause a loop, total devastation of effort. So we enable a security feature called BPDU guard, which keeps tracks of incoming BPDU and disables the port if any BPDU is received on the port, thus protecting the network before a loop is created. And the final feature that we are going to discuss is called ether channel. The ether channel combines the multiple parallel segment of equal speed links up to 8 between the same pair of switch. All the wires or physical connection are bundled into a single logical connection, which ultimately helps to improve the network uptime and speed. To configure a ether channel, we have to use the command channel channel-group and assigns a channel number. On per interface basis, the Ethernet, the Ether channel load balances the traffic on the basis of flows. The flows of connection between one device to another. For example, a PC connects to a specific printer, so it uses a defined physical connection to transmit all of the frames between these two devices, which can further be changed or classified by using the command port-channel load-balance, and if we put a question mark at the end of this command, the switch will give all the options. By the way, the most common options are on the basis of source MAC address, destination MAC address, source IP address, destination IP address, and many more. To view the Ether channel configuration, we use the command show Ether channel. It is the most confusing part of the Ether channel that three different types of command is used to configure, monitor, and change the values of the same Ether channel link. So let me recap for you once again. The channel-group configuration command is used to assign a number with mode on per interface basis to make a link assigned to a specific Ether channel group, while port channel is used to configure on what basis the flows should be selected. And finally, the show Ether channel is used to view the configuration. If we pass the command channel-group number mode on, we are going to configure an Ether channel manually, and the number that we just defined should match for all the commands on the same switch, but this number can be differ on the neighboring switch. While we can also make the Ether channel dynamic, which means to automate the negotiation whether a particular link becomes the part of Ether channel or not. To enable automation, we use the PAGP protocol or LACP protocol. The PAGP stands for Port Aggregation Protocol, while LACP stands for Link Aggregation Control Protocol. On the same command, channel-group, a number mode, if we select the mode as desirable or auto, we are using PAGP, while if we selecting the mode as active or passive, we are using LACP. Bundling of Ether channel will only be performed if the two switch with Ether channel enabled is either static, which means the mode is on and on for the both switch. If it is either desirable or is either desirable and another one is an auto. Same goes for LACP. If it is either active and active, if it either active and passive, but the trunk or Ether channel does not forms in case of one switch using the static mode that is on, while another switch is using one of any remaining modes, desirable, auto, active or passive. And yes, the PAGP, desirable and auto, and LSCPs, active and passive, are not compatible with each other. Or if you don't get it, I also want to make it clear that auto and auto in PAGP does not form a channel, and just like that, passive and passive in LACP does not form a channel as well. We are about to finish the overview of our Ether channel. I just want to make you aware that Ether channel is a very sensitive topic. All the changes must be done when the switch is in its downtime, means that the switch must be shut down before changing any configuration. And all of these settings like its speed, duplex, trunking state, encapsulation state, VLANs, everything must be similar. Only then an Ether channel can be successfully formed. And right before finishing this audio/video, I just want to make sure that how the load balancing works. So let's say that we have two switch a switch A and a switch B connected by two fast Ethernet trunks. Normally, when we bring STP in action, the STP's algorithm disables one of the link to avoid a bridging loop between the two switches. The result will be only one link used, which is a very poor optimization or utilization of the available bandwidth, as it is result in bottleneck and reduced network performance. To overcome this problem, we can use two different VLANs using two instances of STP, one for each VLAN, and making a switch route for first VLAN and another switch route for the second VLAN. So by using these methods, we can ensure that the traffic is distributed evenly across both links, providing better performance and redundancy. So hope you enjoyed studying with me. Have a good day. Take care. Bye.